everyone. In this lecture we are going to discuss about pipes arranged in a series or pipes arranged in parallel. So let's first discuss about pipes in series. So in this case, different pipe segments are fitted with one another in series. That means water from this pipe, the first pipe, will go to the second pipe, then third pipe, which is a bent pipe, then again the fourth pipe, which again has a bend, and so on. So this kind of an arrangement is very common in case of water supplies, because it has a large pipe from which a small pipe will come in, then there will be different fittings, different joints, and so on. So to analyze this kind of a pipe flow, the thing that we need to understand is that the total head loss across the total length of the pipe can be obtained by adding the head losses occurring across the individual pipe sections. For example, if we measure the head at this point at the beginning and head at this point, then the head will be, obviously at this point head will be more, and at this point head will be less. So in between the head will be decreasing gradually. Suppose if we try to draw this diagram, that is hydraulic gradient line, then it will be coming like this, and it will be ending somewhere around here with a very small amount of head. Now if we measure the head losses across all these pipes individually, that means this was the initial head. At the end of this pipe you have lost this much head. Now this pipe starts from this much head, and over the length it will have lost this much head again. Then this pipe will start with this much head only, and at its end it will be left with a smaller head, and whatever is the difference, that difference will be the head lost in this length of the pipe. And the same is true for the remaining length of the pipe. So this concept can be used, and one thing that is remaining constant here is that the discharge through all the pipe segments are the same, because whatever amount of water is coming through this pipe, the same amount will go through this pipe, through this pipe, because it is the same line, and through this pipe. So using these two understandings, or these two facts, we can actually prepare two equations, and these two equations will be that if we call this pipe number A, B, C, and D, then total head loss will be equal to HA plus HB plus HC plus HD. Here HA will be F L of A V of A square by 2G into D of A. That means L of A means length of this pipe, A, VA is velocity through this pipe A, and dA is the diameter of the pipe A. Plus again F into LB VB square by 2G into DB, and so on. So this way we can write this equation. Now if you want, you can also add the minor losses, but for this example, because it becomes too complicated, not too complicated, just to lengthy. So for this example, we will simply ignore these minor losses, but if you want, you can also add them in between. That means this expansion loss will be added here, this contraction loss will be added after this, then these bends will be, this bend and this bend will also be added, then again this expansion, this bend, so all these losses will have to be added. So this is one equation that we got. Now the problem is that we know that the diameters BA, DB, DC, D and DD, suppose those are known, the lengths are also known, the unknowns are these velocities VA, VB, etc. So we are considering 4 different velocities in these 4 pipe segments, but we can eliminate all these 4 variables and replace them with one single variable, and that is based on this fact that the discharge through all the pipe segments are the same. That means VA is equal to the discharge Q. We don't have to write QA, QB, etc. because Q is just Q for all these pipes, the discharge. So Q by the cross-sectional area, suppose we'll call it small a and subscript A. So VA is this much, VB is equal to Q by area of the pipe B, and so on. So all these terms will be replaced with Q by the area. So only unknown left will be the value of Q. And if we know this total head loss between this point and the end point, then we can simply solve this equation. So you can formulate any kind of problems using large number of pipes and try to solve them. The next arrangement is pipes in parallel. So if suppose the pipe is going this way and at some point it branched into 3 different pipes, it may be 4, 5 or any other number. So when it is branched into 3 different pipes and then again it is meeting at some other point, suppose this point, so in that case we can measure the head at this cross section and the head at this cross section. So we'll get some head difference between these two. Now if we measure the head difference between for this first pipe and we measure the head difference between this end and this end, then that head difference will be same as whatever we measured in the previous case, and therefore the total head difference across all these pipes will be actually equal. That means HA, suppose, is the head loss or head difference between the two ends of this pipe A, and HB and HC will be actually equal. HA is equal to HB equal to HC. So this is one equation that we have. Now the difference is that in this case all these pipes will share the total original flow which was coming through the main pipe, and their sum will be the discharge. Suppose QA plus QB plus QC should be equal to the original discharge Q. Now again we have two equations, or we can rather say 3 equations, and by solving them we can find out what is the discharge or what is the head loss and all those things can be found out. Now if it may seem familiar because we have already learned this kind of a thing in our electrical engineering or electricity courses, where we add, suppose, a number of resistors like this. So in this case the resistors are the pipes, and the total head difference between all these resistors, suppose between these 2 points plus between these 2 points plus these 2 points, is equal to the total head loss or total potential difference in this case, or the total voltage actually applied over the whole circuit. On the other hand, when they are connected in parallel, then suppose 3 or 4 resistors are connected in parallel, then the head difference, the total potential difference or the voltage, is equal to the voltage across all these individual resistors. So in this slide you can simply compare how they are very similar. Now if we go for some kind of example, so it's a very simple example where we have one tank and another tank. So here water level is slightly above, so head is higher, here head is lower, and the difference between them is suppose H, and this H is equal to head loss, sum of head loss between these two pipes, that is HA plus HB. For the sake of completeness, you can also add head loss at entry, then plus head loss at A, plus head loss at sudden contraction, suppose we call it HC, plus head loss at B, and plus head loss at exit, like this. So, and we can write the formulas for all these head losses because we already know them, whether it is major loss or minor loss, and then again replacing those values of V's, V1, V2, etc. with Q, we can find out the actual value of Q. Similarly, if we have this kind of an arrangement where one pipe came out but it branched into two pipes and then again merged into one single pipe, in that case, suppose let's call this A, B, C and D, then the total head loss we can simply find out by measuring the water level difference in these two tanks. Suppose this is H, so H will be equal to, let's ignore the minor losses because they will just clutter the whole space, so it will be HA plus HB, that means head loss across this pipe, plus HD. Now we can also write another equation where we'll follow this path, then also H will be equal to HA plus HC plus HD, and then we have two equations, and using that we can, by replacing them with the actual formulas, that is FLV square by 2GD, and B will be replaced with Q by A and so on. So using that we can solve these equations and find out what is the discharge through this pipe, through this pipe, through this pipe and through this pipe. So that formulation of the equation, I'll leave it to you. You can imagine any kind of this problem and try to prepare the equation. After you prepare the equation, it's just a matter of solution. Now let's look at some practical examples. For practical examples, it's easy to imagine a practical example for pipes in series because anyway we'll when we are dealing with several kilometers of pipes at different points, we'll have to join those pipes. They may be of different diameters. So this kind of an example is very easy to imagine, and we see it all the time. But the pipe flow in parallel is generally not seen in our household problems, and that's because if we branch a pipe to 2 or 3 branches, then it doesn't make sense to again join them together. Suppose in your household water supply, why would you do that? You'll simply have one main pipe, and from all these pipes, different branches will go to different places, maybe bathroom, kitchen, and so on. So there's no point in again joining them together. But these kind of examples can be actually seen in industrial setups and very commonly in cooling setups. So a very good example is a radiator. If you know what a radiator is, it is something which is used for cooling. Suppose we have a car engine, and suppose this is the best engine I can draw. There will be some pistons, they will be moving up and down and creating heat. So this whole engine block will be this. There will be some bells which will be running the whole car. This whole engine will actually heat up during the process. Now to cool this engine, we'll insert some pipes which will run through the engine block, and they may be parallel pipes, but we are not dealing with this part. But suppose, let's say there is only a single pipe which is running through this engine block, and through this pipe will be transferring water, and those tubes will be moving through a radiator. Suppose we have a tube, and this tube will run this water through a radiator like this. This radiator will have lots of small tubes, metal tubes, through which this water will be passed. Now up to this point, water is coming only through one tube, but as soon as it enters the radiator, suppose there is a place where you divide the whole flow into different pipes, and through these very small metal pipes, water is transferred to the other side. Then this water is again carried back to a reservoir, so from this reservoir, again using a pump, the water is again pushed through this engine block. What happens in this radiator is that the surface area of all these tubes will, because there are a large number of tubes, the water flowing through these small tubes will transfer the heat. Because the water is going through this hot engine block, the water will be heated up, and while flowing through these small tubes, it will be transferring all those heat to the metal walls of all those tubes, and there will be a 1 or 2 fans blowing air into the radiator, and that way those the heat which is radiated out of those metal tubes is also carried away into the atmosphere because of the wind velocity. So this is a very good example of pipe flow in parallel, and the same is also done in case of large dam construction, because as we know, dams are very huge, and when they are made of concrete, since setting of concrete is a exothermic reaction, that means if we have a very large dam like this, which is suppose 50 meters across and 60 meters tall, the inside of the dam, when you pour the concrete, then during the setting, those heat will be generated, and if the heat generated cannot escape, then it will expand and the entire dam may crack. So what we do is, again, we insert lots of metal tubes like this, and through these metal tubes we push water, cold water, and those cold water will absorb the heat from the inside of the dam, and that is again maybe connected to this kind of a very large radiator or cooling tower and so on. So this is one example of pipes in parallel. Now the concepts that we have learned about head loss, they can be used to find out how much should be this power of the pump. That means some head will be lost, that means energy is lost, that means that energy is to be provided by this kind of a pump, and whatever energy is lost, this pump should be able to provide the same energy just to keep the water moving through this loop. So these are some examples of pipes in series and pipes in parallel. So we'll practice some problems in some of the live sessions that we'll conduct. So this is all for now. Thank you.